Okay, when we finished up the notes, we were talking about how to do rice tables to figure out concentrations. Okay, if you have a mixture that's in equilibrium, um, what kind of things can you do to it? Okay, they have something called the reaction quotient. Okay, and a quotient is like an equilibrium constant, but what it does is it uses to calculate what if you're not in equilibrium? What if you've not reached equilibrium? What is the concentration at that point? Okay. So if we want to calculate Q, they call it, for one of the compounds, one of the, substitutes in your pressure or one of your reactants, one of your products, you can actually figure it out even if they're not at equilibrium. Because when we did a rice table, we figured out the initial concentration, the change, and then what happens at equilibrium. Well, what if it's not at equilibrium? What if we know what the rate is, but we don't know what the concentrations are? Um, if you want to compare them, okay, when they're at equilibrium, okay, you can see up here we have at equilibrium, we have Q and K. Okay, they're moving forward still. Um, in nature, sometimes we get it going the other way where we have reactions. Well, normally, we think of reactions proceeding to products. And at that point, when that's happened, that means your Q is less than K. This is the constant. This is when we're looking at them at specific times. Obviously, when they're in equilibrium, they equal each other. So if we're trying to find a concentration of a reactant or a product, it's Q, and it's at equilibrium. It's what the natural equilibrium constant is. But if we're in nature and we're going from reaction and we're going backwards, where we're taking the product and we're breaking it back down into the reactants, now Q is greater than K. If we're going from reactant to products, it's less than K. And you can calculate this, and I guess that's probably what I should move to because I'm probably confusing you. If I want to figure it out, okay, if you know what the equilibrium constant is, okay, you can find the equilibrium concentrations from the initial. That's what we did based on stoichiometry. That's what a rice table does. But what if we're not at equilibrium? Okay, you can set up a table similar to that if you're not at equilibrium by using X. You use the variable X in place of concentration and the change of concentration, and that'll help you figure out their concentrations when you don't know, when they're not at equilibrium. Okay, so you can use the rate, and then we use variables, and then we'll solve for that. So if you look, okay, we have the K sub C. We know what the equilibrium constant is at 298 Kelvin. That would be 25 Celsius. Anyway, it's 0.059 for the following reaction. Okay, here we got our N2O4 and NO2. Okay, so we know what the equilibrium constant is. We've got the initial concentration of our reactant, and we don't know what our product is. We can use this information to fill in our chart. Okay, so what we'll do, here's our race table. We know what this is, the concentration. It said the original concentration is 3.5. And we know that NO2 is 0 because it's our product. Okay, well, if this is, we don't know what this is, we don't know what the change is, we know we're just going to use X. And again, if it's a reactant, we know it's negative X. Well, using stoichiometry, 2, so this is 2X. So the change in this is going to be 2X because 0 minus that. And this one is going to be 3.5 molar minus X. Now, when we set these up, did I set this up? Okay, we set it up like this. All right, we know what the equilibrium constant is. Okay, we've got our product 2X, and there's 2 of them, so it's to the second power. And then we've got this is just to the first power. Now to solve this, you guys, you're going to have to use like quadratic equations and some craziness, and you're going to have to use square roots and all that. Okay, and the other thing is, if you look in your book, it'll tell you to basically ignore this because this is a really small number. It really doesn't affect it that much. Well, if I tell the math teachers, just ignore this variable, they'll probably smack me. So all I'm going to have you do, because I don't really need, I mean, yes, we use a lot of math skills in chemistry, but I don't need to know your advanced math skills. So if you set it up like this, I would be perfectly satisfied. Okay, the rate and then the product over this. Again, if you want to solve this, you're going to basically ignore this, and then you're going to have to divide, and then you're going to have to find square roots and all that. And I don't expect you to have to do that. This is all you need to do for me. Okay, Okay, if I actually set it up, here you see, to solve this equation, you assume that 3.5 minus x is close to 3.5, so you just ignore the x. Okay, so I take this and I'm going to subtract 3.5 from this side, and I get this, and then it's x squared, and then I take the square root. Again, I don't expect you to have to do all those steps. If you left it like this, I'm happy. And I actually have, like in your assignment, after we're done with this, I actually did the first one, I think, to show you how to do it. Again, this is good enough for me. If you want to solve it, please feel free. I'll tell you if you got it right or not. But I'm okay if you just leave it like that, okay? Okay, so at equilibrium, then I can take this number, x, and I can plug it back in the table. Okay, now I got to go back. Oops. Okay, I'm going to plug, I found x, I'm going to put it in here. And so now I'm going to find at equilibrium. If I want to figure the change, I would just take 3.5 minus that number, and I'd get x and then 2x. And that would give me their concentrations. That would give me the change. Again, I'm not going to worry about it if you know that, if you want to do that. You don't have to, okay? But this is what it would be. So I would take 3.5 minus this number. That would give me the change in N2O4, and then this would be the 2 times that would give me this. And again, I'm not going to have you worry about that because then you have to solve for x. If you want to, if you've got those grand math skills, but please don't tell any of the math teachers I'm telling you to ignore a variable. I'll probably get smacked. So anyway, that's why I'm just going to set it up like that and we'll be good. Okay. Now there's something called the K sub P. This is the constant when we add pressure into it. Because remember, we're working with gases. So we can compare the equilibrium constant based on concentration, and then we can do one based on pressure as well. Okay, because if you change the pressure, you're going to change things. Okay, so for gases, we know, if you remember back to last semester, the ideal gas law is pressure times volume equals N, which is the number of moles, times R, which is the gas constant, 0.00821, times temperature. Okay, well, if we manipulate this formula, this is what it equals. Okay, the equilibrium constant, the K sub C, times R, the gas constant, temperature, remember it's got to be in Kelvin, and this is the change in moles. And the way we do that is we take the moles of the product minus the moles of the reactant. Okay, so that's the result. That's the formula you use to find K sub P. So once you find K sub C, it's really easy to find K sub P. You just plug in the numbers. Okay, so, and again, the change in N, this number up here, is actually the moles of the gas product minus the moles of the gas reactant. And I'll show you an example. Okay, so here's our formula. Okay, and again, I put that in there again, probably because I covered it up here down here. Sorry about that. Gas, moles of product minus gas or reactants. So if we're using that one we did, this was our K sub C. It was given to us. Here's our R, 0.0821. Temperature, if it was 25, it'd be, I think it even says in there 298 is the temperature of Kelvin. It's got to be in Kelvin though, because we're working with gases. And then we get 1. And the reason for that was we have 2 moles of product gas and we have 1 mole of reactant. So that's where the 1 comes from. And then you just multiply and divide and you get your answer. Okay, so that's how you find K sub P. You take your K sub C, which is either given to you, you have to find gas constant, temperature in Kelvin. And again, this is moles of the product minus moles of the thing. And if we go back, I'll go back here, sorry. Here we go. Here's our, we've got 2 moles of this and 1 mole of this. That's where we get our 1 mole when we're doing our K sub P. Okay, so again, that's all we're going to do for this part. The last part of this chapter deals with what happens when we add a stress. By a stress, I mean what happens if we add more product, or if we add more reactant, or if we add pressure, or if we add temperature. So we're going to talk about that after, but first we're going to do a little bit more rice problems and some K sub P. And again, I have some examples for there. You'd only have to show me how you would set it up. So this is all you'd have to show me. Okay, you don't have to actually solve for it. I'm okay with that. Because again, I don't really like the fact that you ignore a variable. And again, math teachers will probably kill me if I did. So that's where we're going to leave it at that. Okay, so that's all we've got for this part. We'll finish up. Again, we'll do some K sub P's. And then we'll finish up with this chapter with Le Chandeliers, which is next. And I'll talk about that later. So So much for this chapter.